All right, welcome. Today, we're going to unlock the blueprint for one of the most important families in organic chemistry. Seriously, these molecules are everywhere, from medicine cabinets to huge industrial plants. And we're going to break down exactly how we can identify them, build them, and even transform them.
So think about this for a second. What could antiseptics, solvents, and even anesthetics possibly have in common? Well, the answer is they all belong to the family of molecules we're digging into today. They might seem totally different, but they share a common architectural feature that ties them all together. So, okay, let's dive in and see what that is. Okay, so first things first, let's meet the three core members of this molecular family. And you're going to see they're all defined by one really simple thing: where they decide to put a single oxygen atom. First up is probably the one you've heard of, the alcohol. The rule here is super simple. If you see a hydroxyl group, that -OH group, literally just stuck onto a saturated carbon chain, that means a chain with only single bonds, you are looking at an alcohol. It's kind of the foundation of the whole family. But here's where it gets really interesting. It's all about location, location, location. If you take that exact same OH group, but you attach it directly to that powerhouse of a molecule, the benzene ring, its properties change dramatically. That ring makes it more acidic. It's not an alcohol anymore. It's a whole new ballgame. We call this a phenol. And then there's our third member, the ether, which completely flips the script on what that oxygen is doing. Instead of hanging off the side of the molecule, the oxygen atom becomes a bridge, linking two carbon-based groups together. Just picture it, an oxygen atom with a carbon group on one side and another on the other. So let's boil it all down, right? It all comes down to how and where that oxygen atom is placed. Is it hanging off a carbon chain? That's an alcohol. Is it sitting directly on a benzene ring? That's a phenol. Is it acting as a bridge between two groups? You've got an ether. This one simple difference changes everything. Okay, so we can spot them in a lineup. But how do we actually build them? How can we construct the exact type of alcohol we need? Well, for that, chemists have this master tool in their toolkit. And that is the Grignard reagent. Its superpower is its ability to create new carbon-to-carbon bonds, which is huge. Think of the R part, that's our carbon group, as being super negatively charged. It's like one end of a magnet, and it's on the hunt for a positively charged carbon to snap onto, letting us build bigger and more complex alcohols. And the best part? The process is a super reliable two-step sequence. It's almost like a recipe. First, you take your Grignard reagent and you add it to your starting molecule, something with a carbon-oxygen double bond. Then, for step 2, you just add some acidified water to finish the reaction, and voila, you get your alcohol. It's a really dependable method. Okay, and this is where the real beauty of this system comes in. There are rules. Rule number 1, if you start with formaldehyde, which is the absolute simplest aldehyde you can get, you will always end up with a primary alcohol. No exceptions. It just works every single time. Rule number 2, if you switch it up and use any other aldehyde, one that's a bit more complex, the Grignard reaction will always give you a secondary alcohol. Again, it's completely predictable. The starting material determines the outcome. And you can probably guess rule number 3, right? If you start with a ketone this time, you'll build a tertiary alcohol. See the pattern? It's so predictable. It's just a totally elegant way to build exactly what you want every single time. So what's the big takeaway here? It's that by choosing your starting ingredient, whether it's formaldehyde, some other aldehyde, or a ketone, you have total control. You are the architect of the final alcohol you want to create. This is basically molecular architecture at its most fundamental level. So cool. So building from scratch is one thing. But what about remodeling? These molecules aren't just static. They can also be transformed into other incredibly useful compounds, turning one type of molecule into another. We can do this using a process called controlled oxidation, and you should really think of it as a super precise molecular makeover. We're not destroying the molecule, we're just skillfully remodeling it by taking away a couple of hydrogen atoms, which completely changes its identity. So check this out. Here's how it actually works. You start with a secondary alcohol. The reaction comes in and just plucks off two very specific hydrogen atoms, one from the oxygen and one from the carbon it's attached to. A new carbon-oxygen double bond forms in their place, and boom, just like that, our alcohol has become a ketone. This just goes to show you how interconnected everything in organic chemistry really is. It's all about transformations. You can take one functional group, like an alcohol, and with just the right reaction, you can skillfully remodel it into something new, like a ketone. It's this constant cycle of building something up and then changing it into something else. So you might be thinking, why does mastering this molecular blueprint even matter? Well, it matters because being able to build and transform these molecules is, and I'm not exaggerating, foundational to our modern world. From the research lab to our daily lives, these things are absolutely everywhere. I mean, just think about it. Take ethanol. It's a fantastic solvent used in paints and varnishes. Then you've got phenols, which are used as antiseptics, like in throat sprays. And ethers? They were actually some of the first general anesthetics ever used. And that's why, for example, industrial ethanol is often denatured. They mix in other stuff to make it undrinkable, but it keeps all those useful properties we need. And you see, this constant cycle, building up, breaking down, transforming and retransforming, that's what makes organic chemistry so incredibly powerful. And that question right there on the screen, what turns a ketone back into an alcohol? Well, that gets at the very heart of this idea. For almost every reaction, there's a way to go backwards. Thanks so much for joining me for this explainer.